Thanks everybody for showing up. It's a pleasure to have Anthony Chen here from Caltech. He's a PhD student working with Fernando Brandao and Joel Trop in math and physics. And he works at this intersection of quantum information theory and quantum dynamics. So using tools from matrix concentration, thermodynamics, and quantum algorithms. So I think this should be a very interesting talk. So Anthony, looking forward to it.
Thanks for a nice introduction. So I guess I should just begin. Today I'll be talking about the recent work about a quantum algorithm that will propose the thermal state of your quantum system. This talk is based on a few works that one is being currently updated, the other one will come out very soon, so we might just wait a little bit. And let's get started. All right, so the task we're considering today is to sample Gibbs states. More precisely, you're given a quantum Hamiltonian and also a quantum computer, and the goal is to prepare the thermal state. The thermal state is an object you can take from the physics textbook. It's also called a Gibbs state. It's a density matrix which is diagonal on the energy basis. And these energy states are weighted by this Boltzmann factor exponential minus beta E, where E is the energy. If you make beta equal to 0, this weight is the maximally mixed state. If you make beta very large, then this is the ground state. Okay, so you want to go through a lower energy state. And that's our goal. And let me motivate this task by a very practical usage of quantum computer, which is quantum simulation. It's currently a very popular candidate for practical quantum speedups. To very quickly review, the goal of quantum simulation is to mimic properties of physical systems using a quantum computer. The question you can ask are including, say, ground energy or some dynamic properties of your material or some chemicals. People have identified the following key subroutines that you need to do in order to successfully simulate your material. And among these, the most mysterious one is the preparation of the initial state. And so indeed, if you look at some of these proposals by companies that they try to get a complete resource estimate of such a quantum chemistry or material simulation task, there's a very, very big mystery of how expensive it is to prepare an appropriate initial state. Okay, if the number is 1 million, then it could really impact whether quantum computers are really useful. Okay. So it turns out this mystery of low energy states is there for very good reasons. You can get very different answer, depends on who you ask. From a complexity theory point, this problem feels very hard in the worst case. So indeed, in the worst case, this is QMA hard is some kind of version of quantum MP hard that we don't even expect quantum computer to solve efficiently. That seems to be a bad news. However, if you ask physicists, what they would tell you is that you can believe in thermodynamics. So if you just put your system into a fridge, as physicists have been doing every day in their lab, thermodynamics tells you it is naturally in their lowest energy states or the thermal state. It just depends on the temperature. So you see a big difference between this worst case and suppose the average case behavior that we see in daily life. And it really boils down to which assumption that you want to use to make this distinction. There's even another angle that if you're just using classical computers, there even exists very empirically very efficient heuristic classical algorithm that could sometimes solve this problem. So you now already see there's a wide range of landscape of what could happen in terms of low energy states. And in particular, if you want to argue that quantum computer can do very well, then you kind of want something in the middle, that maybe it's quantumly easy, but classically hard. So this has been a very active direction that many people are working on. And And the thing we want to do here is really to draw the right assumptions and algorithm that allows us to cut these different regimes. Okay. So that's the motivation. And our goal for today is to provide a new angle on the state preparation problem by proposing a so-called Monte Carlo style quantum algorithms. Okay, what do we mean by that? It is a very close cousin of classical Monte Carlo methods or classical Gibbs sampling. So classical Monte Carlo, what you do is usually use it initially for physics simulation of Ising models, but later on has takeoff and have wide application is also a problem you can think about. Okay? The spirit here is that there's an algorithm, it's easy to use, there are not too many parameters to tune, and then someone gives you a problem, you can just run it and see how good it works. And I want to make analogy that the algorithm we propose for today is the quantum analog that also have this robust and universal feature that you can just look at a quantum Hamiltonian and throw it to it and see how well it works. Maybe it works, maybe it doesn't work so well, but you can always try. At the same time, I also want to draw a connection to physics. And in fact, the algorithm we propose are deeply rooted in physics, especially thermodynamics. Okay, in the dynamics, when your system is interact in an open system with a thermal bath. Therefore, understanding our algorithm also leads to understanding of physics of these various recent fields of recent interest. And so that will roughly be the picture we're having today. Right, and let's begin our talk by reviewing the classical Markov chain Monte Carlo methods. The spirit there is that you want to implement a Markov chain that converges to the Gibbs state. If you look at this simple example, it's a random walk on a line. There are 4 energy states from 0 to 3. And you can calculate that the Gibbs state is going to be some exponential decaying function with most of its weight at the lowest energies, which is 0. And so you can convince yourself that if you want this Markov chain to go to the 0, then these arrows should have a stronger bias toward the lower energy states. However, more precisely, if you want the stationary distribution to be the Gibbs state, then you have to choose this transition weight a little more carefully. And a very powerful and very general recipe is called detailed balance. So what we're going to do is to impose that at the stationary state, the flow forward and backward cancel out each other. Okay, so this is the equation I wrote down here. And then you can just invert this equation and check that indeed the above number satisfies this condition. Therefore, this Markov chain above indeed converges to the Gibbs state. And since this problem is so simple, we can also calculate how fast this makes. So this 1D random walk. However, the power of Markov chain Monte Carlo is that it works beyond this very simple, almost contrived example. Okay. So now the key is that how do we impose this detailed balance for more general and very complex Markov chain? For this, let's look at the representation of the transition matrix. Okay, so let's now sort the configurations by their energies, U1 and U2. And then detailed balance in this picture is some kind of symmetry of this matrix. It has to obey this particular rule of that if you just flip across the diagonal, then these two are related by this number. And this number depends only on the energy difference. Well, this looks kind of delicate because the symmetry that if you fix the above triangle, then the lower triangle is also fixed. So it's very delicate. However, there's a very robust and almost a blind way of imposing detailed balance. It's really the insight of Markov chain Monte Carlo method is that you can do this without knowing the entire matrix. You can do this, quote unquote, locally. Okay. So what you're trying to do is to start with a symmetric Markov chain. And then you're going to sometimes reject one direction of the move. Once you do that, you penalize one of these transitions, which is in color red. And then you end up getting this detailed balance condition, and you can tune the temperature parameter beta. This turns out extremely powerful, extremely robust. You can do it in many cases. And most notably, this came from the Metropolis Hasting algorithm that's still being applied today. To get a very concrete feel, here's the input to your algorithm. As a user, you only need to specify a Hamiltonian, temperature, and a set of jumps. And you need these jumps so that it can traverse the landscape of the Hamiltonian. For concrete examples, consider Ising model on some spins. Okay, these spins could be up or down, plus or minus ones, and you can specify some pretty arbitrary coefficients, these j's. So you put that in your computer. And then now you specify the jumps, and quite often you can take this to be local flips. And more fancy choices also works, but it's a very iconic example. So here's a schematic picture of the algorithm. Now you can start with some pretty generic initial state that you can efficiently prepare. And then you iterate the following Markov chain. You randomly flip one of these spins, that's your jump. And then you check that whether the energy has decreased or increased. Both could happen. And if it decreased, that's good news. Let's accept and move on. If it increased, that's bad. And sometimes they have to reject this move to ensure detailed balance. And here by reject, I mean that you would just undo the jump and then do the whole thing again. Okay. So now this is a Markov chain, and this is a well-defined algorithm. You can just wait for this algorithm to converge. You might not always know how fast it converges, but you can always try. And then if it actually converges, this will be the Gibbs state. That your output is going to be a sample from the Gibbs state. All right, so that's a classical Monte Carlo. The reason why I'm bringing this up is just is that that really is what we want to do, but try to push it in a quantum case. So here's a list of things that you want to generalize. You want to generalize spin configuration to entangled quantum states. You want, instead of a classical distribution of Gibbs states, you want to have an incoherent mixture of this Gibbs weights on the energy basis. The Hamiltonian now could be non-commuting. Okay, so these energy eigenstate could be pointing at pretty generic directions. It could be very entangled. And now the jumps, instead of spin flips, now you can do all kinds of local poly rotations. You can also choose more fancy choices, but this is enough. And now the challenge is, how do you design an algorithm in the spirit of Monte Carlo that is also widely applicable and easy to use, that has similar properties? So far, there seems to be lacking a satisfactory algorithm with the guarantee that it has detailed balance and a correct fixed point. And let alone the discussion of mixing time without defining such a map. Okay, so today we're going to fill in this blank on the corner, and we'll discuss it separately in two parts.
One question, Anthony. Sorry.
Yeah.
So when you said this part 1 and part 2 is missing, do you mean local flips are missing in the quantum world? Because there is a Davis generator and all, right?
Right. So I say they're unsatisfactory. So
Okay.
there are lots of proposals, but each of them has their own issues.
Okay. All right.
Yeah.
Thanks.
Thanks. Now let's dive into the first part of how you go about designing such an algorithm. So people have been trying this for a long time. So one thing you can do is to do that. Oh, maybe I can just do Metropolis on an energy basis. That's a reasonable try. And all that you're doing is to replace the spin configuration with each individual energy eigenstates. And this could kind of work formally. You just replace Z by the projectors, and then you replace this transition by the amplitudes. Right? So the right-hand side is this natural quantum transition rates. It's now some the amplitudes between two states and the operator and this jump operator. So in this picture, if you want to look at this transition matrix that's sorted by energy, it would suggest that you want to look at this band of the same energy transition energy difference omega. It's like the classical analog. Okay. So this seems somewhat reasonable. However, there has been severe challenges that's intrinsic to quantum mechanics. What are they? So algorithmically, the rejection step turns out being quite delicate. Classically, you can easily reject a move just by cloning the previous state. Or you can unjump and go back to the previous state. You can do this many ways. But quantumly, you cannot measure the state, you cannot collapse the state, and you also cannot clone the state. So that becomes a little more, I have to do this more carefully, you have to cook up some algorithm that does this job. To some of you, you might have recognized what this algorithm is doing. Myriad watchers. And the problem is that if you want to do this algorithm, you also this problem becomes very convoluted once you consider the challenges below. Okay. These challenges are that fundamentally, energy measurements is uncertain. It's very difficult to make very precise energy measurements. Usually that invoke an exponential cost. And that brings lots of issues. So most importantly, detailed balance is broken. Okay, so if you have worked with Markov chain, we really, really love detailed balance. It has so many nice properties. And now if detailed balance is broken, how do you even know the fixed point is the correct one? Okay. And second, that's more of a second step issue, is how do you think about mixing in these contexts? It seems that it has to be intrinsically quantum, because now nearby energy could just stay entangled and move around. Because your energy measurements does not disentangle the nearby energy states. And there are lots of attempts to address these challenges. So now let's take a step back. How come there's so many obstacles, but nature thermalized so nicely? How come there's this empirical success of thermodynamics? Right? If you ask experimentalists, they would just put their device into a fridge and lower the temperature of the fridge, then you get ground state or thermal state. It's really robust, really universal, you just do it. So it turns out this nature really knows how to do it, and our algorithm is heavily inspired by nature. So let's see what this nature can give us. The first observation, this is proposed by 50 years ago, this by Davis, is that if you use a continuous walk, since nature is continuous, then this rejection step is also automatically resolved. You don't have to do anything fancy. Okay. So the picture is that this quantum process now continuous. So then infinitesimally, you always get these transitions. Right, and now you can take these transitions to be your these favorite amplitudes of A, sandwiched between energy states, the ones that we have been talking about. And now, instead of doing rejection step, all you do is to simply lower the rate of the unwanted transitions. So you really just multiply these infinitesimal transitions by the appropriate weights. In particular, you can choose these weights to satisfy detailed balance, and that guarantees the fixed point as Gibbs. Yeah, so the point in this slide is that if you have continuous time, somehow things are better. You don't have to worry about rejecting this rejection step in discrete metropolis. And of course, this doesn't solve every problem. This was a 50-year-old proposal. And there they make a very strong assumption that essentially you can measure energy very precise. But then you can really refer to the precise energy omega, this very precise band of transitions on this picture. So we still have work to do. But this ends up serving as the essential intuition that leads to our algorithm. To give a little bit more of a context, these so-called continuous time random walk in the quantum world are called Lindbladians. It takes this general form. Okay, this is what it is. You can choose various kind of operator K that would drive the transitions, the infinitesimal quantum transitions of your system. And what you get in the end, when you act this Lindbladian on your quantum state, is a continuous family of Markov of states that's parametrized by exponential LT. Okay. It's different from unitary dynamics, as these maps could have a fixed point that just shrink every input state to one fixed point. So that's possible. Okay. And for those of you who are more familiar with quantum channels, this is really the continuous versions, and you can see this cross operator looks kind of similar, but now it has a second term. Now we're ready to describe the proposal of ours that we propose the Monte Carlo style quantum algorithm in the form of Lindbladian, which is continuous quantum random walks. We're able to efficiently implement a Lindbladian whose fixed point is approximately the Gibbs state. In other words, this is in the very same spirit as Monte Carlo, that it's very universal. You can just plug in a Hamiltonian, and then you can run it. You could have all kinds of mixing time. Sometimes it works, sometimes it fails. Whenever it works, you celebrate. And it's also very nice that there's almost no fine-tuning required. It's very different from variational algorithms. That here, there's not that many parameters you can tune. You just choose the jumps, and often this doesn't quite change the behavior by too much. Like if you usually some generic choice suffices. For example, local poly flips. Further, we believe our main results is the right way because our formalism directly generalized to many other settings. Our formalism is compatible with Segati type speedup, that you can quantize our Lindbladian to obtain a purified version. You get some kind of quadratic speedup, and that which prepares the purified Gibbs state. Also, for physics, our argument applies to many physically derived Lindbladians. So we can just look at some Lindbladians physicists derived in their paper and say that, hey, this guy actually have the correct fixed point.
So just to clarify, the input to your algorithm is a Lindbladian, and then you are able to implement that on a quantum computer. Is that the message here?
The input is the Hamiltonian. And
it's Hamiltonian, that's it.
Algorithm, which is Lindbladian, based on the Hamiltonian.
Oh, I see. Okay, got it. Okay,
it's very similar to Monte Carlo. You have an algorithm that depends on very few simple things. So that's the next slide. All right, so now let's look at our main result. As a user, you just choose the Hamiltonian temperature and some set of jumps, for example, local polys. That defines you a Lindbladian, has the following nice properties. The fixed point is correct up to some controllable error epsilon. The algorithm is efficient as long as it mixes quickly. Okay. So this algorithm emulates the Lindbladian evolution, and then it converges after some time. So in general, we don't know what this mixing time is. It largely depends on the system, But heuristically, you might guess that if things thermalize nice in nature, then maybe this mixing time is not going to be crazy. Okay, but that will be another subject of study. Yeah. The message here is that this really is a version of quantum versions of Monte Carlo. Right? You have right fixed point, and then you have some guarantee as long as mixing time is not crazy, and you can always run it. Any more questions? All right, so now let's talk about how we get to our results. And here's the secret sauce that make everything work. The key object that we identify is this Fourier transform of operator evolution. Okay, so it's these things on the top right, and this A omega. So let's look at this very carefully. So first, this A of t is defined as the Heisenberg evolution. This is something that you have found in physics textbook. It's very natural in quantum mechanics. Okay. What it does essentially is to add phases according to the energy difference. Okay, so from here you can explicitly see that this really diagnoses the energy differences. Okay. Mathematically, you can think of it as some version of Fourier integral that from this continuous case, but now you do it discretely, and you also put some weight. So now let's unpack this secret sauce. So what we're looking at here is really a boosted Fourier transform. Because once you tune this function f correctly, it acts as certain boosted phase estimation or boosted Fourier transform with a tunable accuracy. So pictorially, if you can do Fourier transform perfectly, then you can access these transitions at precisely energy omega. However, that's really expensive. You cannot really access quantum energy perfectly. And what you get here is a compromise that you will have to have some uncertainty. And as a user, you can tune that uncertainty. And that will lead to different accuracy of these energy estimates. Okay. So it really is just somehow like a smooth version of these bands with some uncertainty in their energies. This object is also very nice that it has a very, very simple circuit. Yes, all you need to do is to input a Gaussian weight wave function to control put your weights on your time register. And then you just time a register to control the operator evolution, and then do a Fourier transform. And the circuit really just gives the things above. Okay. And once you have this component, you can use all kinds of tricks to generalize to more complicated objects, such as Arlen blocking. But this really is the building block. Do Fourier transform in this way. One more nice thing about our construction is that this Fourier transform operator has certain exact symmetry. This is more technical, but however, once you have this exact symmetry, it somehow serves as a stepping stone towards detailed balance. To draw an analogy to a classical case, there you also need to start with something that's very nice, that's reversible or symmetric. And then you can do all kinds of ways to do rejection to get detailed balance. It's very similar here. That somehow in a quantum case, once you have this exact symmetry, things becomes very nice. And it will lead to detailed balance that we'll talk about in the next slide. Okay, so now I have told you how I construct Arlen-Plottians. One more thing that we have to do is to argue that this has the correct fixed point. And that requires a notion of approximate detailed balance that we're not able to find somewhere else. So we just define it in this way. It looks complicated. It has to deal with some norm of superoperators. But morally, what's happening here is you just want to get a sense of how non-Hermitian this is. And indeed, if you make delta 0, this recovers detailed balance and some certain some self-adjointness of this map with respect to the stationary distribution. In other words, the properties of detailed balance, such as the fixed point, is robust once you use it in this norm. The error propagates in the following way, that you have the error in terms of a fixed point as roughly the mixing time times this approximate detailed balance error. Intuitively, approximate detailed balance is some kind of error per time. And then once you evolve for some time, this error could accumulate, but as long as your algorithm converges quickly, it gives you the right answer. Okay. And then we can calculate this delta parameter. And for Lindbladians, this is roughly beta over the resolution or the time, cost of time. So in other words, to make approximate detailed balance nearly 0, you have to pay to have a long evolution time. All right, so that's our construction. So I want to pause and take questions very quickly before I move on to the next part.
So I take it in the circuit, f of t was your Gaussian, right? That was the width to which you you spread the operator.
Yes.
And somehow then you're looking at a Fourier transform on the time somehow, and that's giving you something interesting. So can you say a little more about the intuition there?
Right. So what you're doing here is a Fourier transform. If you put different f, it gives you different f tilde. You're basically doing Fourier transform on this function f. If you put in Gaussian, in the Fourier domain, it's also a Gaussian. So it means that it's nice in both time and energy. It's very concentrated in time so that you can efficiently implement it. You don't have to worry about the tail. It's highly concentrated in energy so that the energy is very accurate. You're basically pretty confident that your energy is within this interval. So Gaussian is nice.
Just quick question. Is it correct to I'm just trying to recall this. So was the Davis generator, etc., the prior constructions were this construction without the Gaussian weights? Is that correct?
Yeah, you can say that. However, so yes, you can think of Davis generator or all kinds of its variants as putting the plane, just making f of t constant.
Right.
That's one way
but
of
then
looking
there was energy uncertainty, right?
And there's a huge energy uncertainty. I think will just make the scaling much worse. It's still kind of work, but historically the Davis generator initially just take t equals infinite. You just allow yourself to resolve everything exactly. That's why it's not solving the problem. And then to have a finite time version, it's not so clear. And in fact, so people have proposed something like this in a physical way to kind of derive it in some way. But the nice thing is that our entire algorithm proves that these constructions satisfy approximate detailed balance, and prove that these physical construction also has the correct thermodynamic properties with the right fixed point.
Yeah, thanks. There are some questions in the Q&A. One question is, does the mixing time also depend on beta and inverse temperature?
Yeah, so exactly. So I have sweep a lot of things into this mixing time. Mixing time is a function of a Lambdadian, and then this Lambdadian depends on so many things. So yeah, it's a horrible object. Maybe sometimes you can get analytic control, or maybe sometimes you just do numerics because it's a well-defined thing. It's a function of the Lambdadian. It's similar to Monte Carlo. Like you never know your mixing time unless you can prove it in some circumstances. But you can always try and see if it works.
One quick question. For the moment, do you have like an estimate of how this mixing time scales with, I don't know, beta or system size or these kind of parameters?
It's a very hard question.
I know.
Yeah, I mean, depends on assumptions. Like maybe if you set out a problem correctly on like a spin lattices, maybe you can try to use some of the existing philosophy, like this decay correlation stuff, to try to prove this mixing time. There's going to be lots of epsilons and delta flying around.
Okay, thanks.
Yeah.
And one related question, if you don't mind. So let's say the Lambdadian without the Gaussian weights was fast mixing for some reason. Would these changes still keep it fast mixing, or could things totally widely change?
So as a physicist, I would say they're probably all the same. But to prove it is not obvious because you just have a different map. The expectation is that when you have these fat tails in Fourier space, you just incur lots of unwanted transitions because sometimes you get your energy very wrong. And then the fixed point would just be kind of far away from this fixed point, or the error scaling is going to be worse. Gaussian is just really nice that you get roughly the energy you want.
Could I ask just a naive question? So if you apply this to a classical spin system, what is the classical algorithm that you recover?
So if you start with classical input and then run this is probably very similar to like some like Glauber dynamics, I believe. But if your input state of entanglement, then we don't know what happens.
Thanks.
Yeah. Cool. Let me now move on to the second part of the talk. We will give certain mixing time estimate since we were curious about the mixing time. And here this is quite a complicated thing. As you know, this mixing time, even in classical cases, is not easy to estimate. And here we rely on a strong physics assumption. It's called quantum chaos that I will define further. And in that case, you can at least get a grasp of what's happening in these very complicated quantum Markov chains. And in the following will be very high level, even though there's a proof. I basically didn't write down any quantitative statements. I just want to highlight the idea. So intuitively, whenever you write down this finite time or like this Markov chain with energy uncertainty, you should think of it as a semi-classical random walk. Okay, so you try to import as much of classical intuition you have. So it's trying to do some random walk on an energy eigen basis, but now you could have some entanglement between nearby energies. This entanglement exists because your quantum initial state could have entanglement, but also that since you cannot distinguish energies, these jumps can also preserve this entanglement. However, these jumps kind of know the energy because if the energies are far apart, so then it's semi-classical in the sense that if energies are far apart, it's incoherent, but if energies are nearby, it could be coherent. And when you apply these jumps, you can think of moving these classical probabilities around while within nearby energies, you can rotate the vector without disturbing it. That's possible. Okay, so at a very high level, if you want to prove thermalization, essentially you want to understand how to get rid of these this coherence. Because in the end, you want something that's a mixture on an energy basis. You have to break all entanglements. Okay, so this doesn't seem easy to prove. And we're able to argue that this is possible in polynomial time, assuming a strong assumption from quantum chaos. So there's going to be lots of physics parameter flying around, so I just drop all of them. I just want to get to the intuition. Okay. So what is this quantum chaos assumption that seems so powerful? Here it is. This is proposed 20, 30 years ago by physicists. It's called Eigenstate Thermalization Hypothesis. It's not quite a hypothesis, more of a condition that it describes something about the operator. So you take a Hamiltonian and another operator A, and this ETH condition says the following. Okay, this condition holds if, for all physical purposes, we can replace the near diagonal band with typical sample random matrix. So morally, what you're doing is that you have some very complicated looking matrix, and the physicists just say, well, why not just treat all of them as random samples from random matrix? Hey, mathematically, this might feel a little awkward of what we really mean by replace, but operationally, it just means that when you do the calculation, you just treat these guys as samples of Gaussians. And it allows you to do calculations. And in fact, lots of physics calculations are done in this way. Okay. Again, the picture is that you now go to the energy basis and look at these transitions. And ETH tells you that if you stay near the diagonal, then these transitions are basically random matrices. It's very densely connected and nearby energies. Okay. So don't ask me where this comes from. This is proposed by physicists, and they just do some numerics. That seems to be the case. That seems to obey predictions from random matrix. Hey, today we need ETH for many operators because we have many jumps. We can take them, for example, to be local polys, and we just treat the Gaussians as independent across the different jumps. Okay. So it turns out this is enough to guarantee thermalization or rapid mixing of these quantum Markov chains. The intuition from the classical Markov chain is that you're looking at a very well-connected graph, at least nearby. Indeed, if you look at these matrix elements given by ETH, these Rij and Gij are basically uniform. So if you have an input state, we just spread you out to all these different energies, and it's just very well densely connected. Well, then you can look at some Markov chain textbook to argue that these graphs connect thermalize very, very quickly. But this is entirely classical. What you have to deal with in the quantum case is decoherence, because you can have a very entangled state, but you want to nevertheless argue that it converges to a very mixed state. And to do that, we have to borrow some idea called quantum expander. This idea was first proved by Hasting by considering random unitaries. So he said that, well, let me construct a quantum channel by summing out a bunch of random unitaries. And then he proved that this is indeed a very good expander in the sense that it has a large spectral gap. The second eigenvalue is very, very small. If you apply this channel many times, it very quickly shrink to the maximum mixed state. But as a quantum expander, it just decoheres for any input state. So it turns out you can do similar manipulations, or I guess you can get similar consequences if you assume ETH. So because there's some part of ETH is random matrix. If you use that, you can also get very similar expander properties. And in the end, it gives you this equation that this map we're dealing with is very close to the expectation. Yeah, you can think of it as some kind of concentration statement, but now you're talking about concentration in a very big, gigantic map. Okay, so now let's assume this is true. So now you have proved this using some random matrix theory. It suddenly reduced the problem drastically, and actually becomes a classical random walk. So very nicely, this expected map is completely decohered. It really reduced essentially to a classical random walk on eigenstates. And now you can celebrate because you can open your Markov chain textbook and try to analyze the mixing time of this object. It becomes a 1D random walk on energy. And yeah, and that would be the proof. So you completely understand this classical random walk, and then in the end you relate to the semi-classical object, which seems horrible by ETH. And that's the proof. Okay, so let's finish the second part of my talk. Let me quickly summarize. Today we give a proposal of Monte Carlo style quantum algorithms. The task we want to solve is to prepare a thermal state of quantum Hamiltonians. And let me just reiterate the main findings. In the first part, we give a Monte Carlo style algorithm in the form of Lindbladians. These are continuous quantum Markov chains with a guarantee that a fixed point is approximately the Gibbs state. You get errors because energy is uncertain. And we believe this is the right way of approaching it because our results generalize to many other settings, also leads to proof of thermodynamics. Is also compatible with quantum speedups. Of course, all these Monte Carlo methods, you have to deal with mixing time that you don't always know. And we give argument for mixing time in a particular case of quantum chaos. That's some kind of Hamiltonians. Not all Hamiltonians are like that, but at least you get a sense of what's possible to be proven. And with that, think about at the right time, let me just conclude with some list of future works. Thank you.
Great. Thanks a lot. Thanks, Anthony. So let's see, there's a question from the audience. Let me just allow Finn to talk. Do you want to go ahead and ask your question?
Excuse me? Who is Hamiltonian?
Okay, maybe we get rid of this.
Who is Hamiltonian?
Okay. All right. So is there any other question?
Maybe I'll ask the question. Hello?
Yeah, great, thanks.
Yeah, and very nice talk. Yeah. So I think we briefly talked about this during your visit last week, which is your talk really has two parts, right? And one is for the ground state and the other is for thermal state. And for thermal state, absolutely the detailed balance is important. Yeah, would you clarify the importance of the detailed balance for ground state preparation?
Right. So the question is, how important is detailed balance if you want to find the lowest energy states?
Yeah.
I don't think it's entirely important because these really detailed balances you want a Gibbs state, and then all these analyses are kind of with the Gibbs state in mind. And I think a lot of balance actually could improve a lot if you have gap ground states. It's really because that when you have a gap, you kind of don't really care the energy of your system. You just need to know a state is there. Then a lot of these error bounds actually become loose, and you can get much tighter bounds if you just want to make sure your state is fixed at a ground state. And more practically, like if you really want to run it and you say, I just want to get a ground state, what you can do, you can imagine that you would start increasing beta. Because then maybe, so it's about like how you actually find a ground state, how you get from like a very hot state to a low energy state. That initially, energy errors doesn't quite matter because you just want to get a kind of rough gradient in some sense. But then energy estimate might become more and more important, and you might have to like change your algorithm so that the energy estimates are better. And indeed, in all these processes, beta isn't quite important because you just want to go to a ground state as quick as possible. You might even just set beta to be infinite. But it really depends on the landscape of the Hamiltonian.
Yeah, so the intuition is that although, as you said, this is how nature gets to the ground state, but classically, we know that there are classical algorithms that works faster than applying infinite minus beta h, and to get to solve eigenstate problems. Maybe in the context of quantum algorithms, we can also algorithmically find some shortcuts that does a bit better than nature.
Yeah, exactly. Like we're proposing is just like one of the very first kind of Monte Carlo methods. And classically, there are methods beyond Monte Carlo, but these are just very robust. You can always try, and then you can also even just change the algorithm.
Yeah, I agree. I think this is very exciting.
Does that answer the question? Maybe I forgot something.
Yes. I think this is very exciting.
Let's see, any other questions?
Well, maybe just one brief comment for this. So sometimes in this classical space, you get quadratic improvements compared to like naive Markov chain methods. We also get this kind of Szegedi type speedups. So at least that quadratic improvement is possible when the mixing time is nice. And so that gives you at least a quadratic improvement compared to just like thermalization. With this Szegedi walk, you get a quadratic speedup. And well, I don't know what you get beyond that.
I think a provable speedup is one thing, but just to say, classically, there are better eigensolvers than Power. So maybe in the end, their symptotic scaling is the same, but the practical performance may differ quite a bit.
Yeah.
I had one question. So thank you, Anthony, for the very nice talk. So in part 2, you described this ETH condition, which prescribes some behavior at the level of individual eigenstates, which seems, kind of, well, very strong and, perhaps non-physical if they're not gapped. So is there a way of replacing that by some more analytic condition involving resolvents or something like that, or functional calculus?
I think yes, because eventually, right. So our argument is that, okay, let's make them very nice random matrices, and you do some calculation, and in the end you can get some good results. And if you just trace back, what you really need is just some low moment properties, and especially this expander condition. Like in classical expander, you can construct randomly using lots of randomness to construct expander. But if in the end, some people may just come up with a deterministic construction. And all you need is really this expanding property and this quantum expander property. So it is at least something you can check on a computer, that if you just go to the energy basis for some set of operators, there would be conditions of ETH in a sense of expander that can be just checked by just diagonalizing the entire matrix. Yeah, does that?
Yeah, thanks. Yeah, and I had one more question about part 1. So in part 1, is it true that your sigma t parameter that depends on time? So actually, the Lindbladian changes depending on how long you intend to run it for, and this is somehow related to this non-normality of some operator that appears, right? Or non-Hermitianness of some operator.
Yeah.
Is that essential, or is that do you think that's an artifact of the proof? Like, could there be a version of this which which just works for all time?
I'm not sure. I think one might be able to come up with lower bounds, because like this energy time uncertainty principle is very strong. Like it would seem to me that if you want to get Gibbs state very precisely, it means that you can really know the energy of individual state pretty precisely. And then one might be able to get some black box lower bounds on like how fast you can create this, but I don't have a written down proof. No. My suspicion is that all these states will have errors.
Thanks.
Okay, so there's a question from the audience, Michael. Let me allow you to talk.
Hello. You haven't mentioned quantum Monte Carlo, the algorithm people use to study on classical computers. Can you compare your approach to that? Like, if you were interested in quantum advantage, at least, at a numerical level, you might compare, your version of quantum Monte Carlo to quantum Monte Carlo people use on classical computers.
Yeah, I have not run any quantum Monte Carlo in classically. I don't know that, but our algorithm could, in principle, work Hamiltonians with sign problems. Yeah, because you can really know the energies of your states, and that's really quantum.
Yeah. So I guess I was wondering. So that in that case, what would how much of an advantage? I've heard people talk about in this so far today, this quadratic speed up, but maybe there's an exponential speed up in that case, or
exponential speed up is possible. I don't know how to prove. I mean, at least it's not ruled out, so it's still possible. But then you have to be careful about how you set out the problems and the inputs, outputs, stuff.
All right, thanks.
One quick question. I don't know. So if not, so if the Hamiltonian is commuting, then in that case you can measure energy pretty quickly to good accuracy.
Yes.
Just run phase estimation and all. So in that case, do you need this technology, or just?
Not quite. So yes and no. Like, there are existing Davis generator. That makes a lot of sense. That also implementable. You can define them precisely for the reason you described, because they're commuting. You can fast forward them basically.
I see. Okay.
So yes, so there are these guys that existed, and yes, the point we're making here is that for non-commuting Hamiltonians, something different has to be done, and we do it in this way. Like this operator naturally would like to spread, and then you have to encounter, you have to confront the problem that you cannot measure the energy precisely.
Okay, thanks.
So what is a good example that the problem suffers from the sign problem, but also has a big gap?
Not that I can think about right now, but
because if the problem comes from a frustration over the classical sort, then the gap must be very small, right? Frustration by definition classically means you have a lot of low energy states with a very, very similar energy.
Right. So you also so if you just give me a really hard classical combinatorial optimization problem, I'm not sure if this will give, unless computers solve MPR problems, otherwise it shouldn't work.
There's even intuitive reason to understand why that doesn't.
So sorry, I didn't quite follow. If it's classical, then there's always a gap, right?
But if it comes from frustration, in the sense that they're just a lot of competing states with very close energies, but their solution looks very different. This algorithm, by definition, the gap is very small.
I believe this will get stuck. Yeah, I believe this algorithm gets stuck for hard.
Yeah, well, get stuck.
Optimization.
So really, when we said for sign problems with a sign problem, right, and which is hard, but also has a big gap. So the sign problem shouldn't introduce there's a classical type of frustration.
Yeah, so
It
exactly,
must be a very something different.
Exactly. So you don't want to be like a classical spin glass or classical hard problems.
Yeah.
But also cannot be too nice that classical computer can solve.
Right. Yeah.
Yeah.
So a good example would be great.
Yeah.
So one quick question related to what Anurag was asking before. So for commuting Hamiltonians, you say that you don't need all this machinery, and this would be essentially for non-commuting Hamiltonians. But do you have an intuition of what happens when you have something that is non-commuting, but very close in some sense to commuting? So in the sense that it's just, adding a perturbation to a commuting Hamiltonian or something like that. Of course, a perturbation that doesn't commute. Do you see if your techniques simplify, or if you get some information of the mixing time or something like that?
Yeah, I think that smells to me like this many byte localization problem. So perturbatively it might allow you to get some control at short times. But at long times, the question is that does the Hamiltonian are still localized some way? If things are many byte localized, it means that it remains like basically like these commuting Hamiltonians for a very long time. And that seems a little hard to do. You can make probably some simplifying assumption to put that picture. But it seems that, so naively, if you just plug in some integrable Hamiltonian, like commuting Hamiltonian, and put some tiny perturbation and then plug in the algorithm, I think the operator still spreads. And then this embodiment will just keep spreading and spreading and get bigger and bigger.
Okay, great. So maybe, shall we, Anthony, if you stop sharing, maybe we could go into the panel.
Okay, stop. What should I do?
Oh, you should stop sharing the slides.
I just did.
Oh my goodness. Okay. So, okay, good. You succeeded. All right. So then as the video is getting pinned for the panel, let me just go ahead and introduce the panelists. So, so for the panelists, we have, Angela Cuevas, who is from the University of Tübingen. So she works on, of course, quantum information theory and very appropriately on open quantum many-body systems. And I guess maybe rapid mixing of Laplace Hamiltonian. So Angela, welcome. And we have David Gossett from the University of Waterloo, who works on quantum algorithms, quantum complexity. I guess he and Anurag Anshu, who is also going to be on the panel, did some really nice work on area laws for 2D systems. David also worked on the max cut problem, and most recently on this complexity of the quantum partition function, which is, I think, probably very relevant to this. Great to have Anurag Anshu back here from Harvard University. He of course works on quantum Hamiltonian complexity. You all know about his work on area laws and on the NLTS conjecture recently. And of course, before this, he worked extensively on quantum information theory. So welcome, Anurag. And then we have it's great pleasure that Andras agreed at the last minute to jump onto the panel. And, from Andras is, of course, a co-author of the paper. He's from the Iranian Institute, and he's worked, extensively on quantum linear algebra, on optimization, quantum walks. So maybe we can start with having the panelists talk about give their thoughts about this this paper. Maybe start with Angela. Would you?
Hey, so, well, first of all, I want to say thank you very much for the great talk, because I really enjoyed it. And I already knew a little bit about the second part that you presented, but the first part was really, really interesting to hear about, and I'm looking forward to reading the paper. And yeah, I found it really exciting because it's what you were mentioning, in your list of open problems, and also what you were mentioning during the talk. I think it's really interesting to be able to provide this kind of tools, that allow you to address the sampling problem, the Gibbs sampling problem for non-commuting Hamiltonians. I think this was, for the second part that you were mentioning, the mixing time, like the tools to prove rapid mixing using weak ETH, also for the same case, right, for non-commuting Hamiltonians. This was like a complete gap that was in the field for a while, right? And I find really interesting the possibility of combining tools that are already there to proving mixing times for commuting Hamiltonians with the tools that you have derived here for non-commuting Hamiltonians. So, again, congratulations, and I'm looking forward to reading the paper.
Thanks.
Great. Yeah. Maybe Anurag, did you have?
Sure. Yes. So thanks, Anthony, for really, really nice talk. I was aware of some questions, some very nice results which are already known in the classical world. For example, this connection between decay of correlation and mixing time and so on. I don't know what's your view on whether those questions which are still open in the quantum world, would they change now with your new tools? Would you see some progress in that direction? So that's just very curious to hear your thoughts on that. Also, I had a quick question. I thought that the statement of ETH that you displayed in your slides, I was aware of a different version which says that an eigenstate looks like a Gibbs state locally. So when I read your abstract in the beginning, I thought, oh, are you going to talk about that connection? But it's a different kind of statement. So, I mean, I don't know if you have any comments on that. But those are questions rather than any comments on that talk. It's a very interesting talk.
So Anthony, did you want to address whether these two views of the ETH are equivalent, or are they?
Yeah, so for ETH, they're different. And it appears that, so in the original proposal, it has both parts. One part is the diagonal part, which is the one that people mostly use. So what's saying in the diagonal is that, also that's basically the energy states. It tells you that energy eigenstates, if they're close in by in energy, they basically give the same expectation for the observables. It's basically the diagonal is very smooth. So then it doesn't matter if you take the Gibbs state, which has some collection of states, or just like one state. And that seems to be very helpful for physicists. But at the same time, it's not satisfactory because it doesn't tell you nothing about the off-diagonal part. So it only tells you like a tiny list of entries of your matrix. And I think people just haven't spent too much time thinking about what these off-diagonal things are doing. But what we're saying here is that these off-diagonal things, this really connects to dynamics. And dynamics leads to thermalization and rapid convergence to the Gibbs state. And actually tells you how to get there. Like suppose you have a quantum computer and then you have one energy eigenstate. I have no idea how you get that. But yes, if you have that, then it probably have many properties similar to the thermal state. But the off-diagonal part tells you how to get there.
I see. Yeah. So here's a question. Let me try to make a statement and let me know if that's right or not. So here's a way to sample from Gibbs state, assuming this other version of ETH, which is take maximum state, measure the energy. If you get the energy in the right range, then ETH would tell you that, well, that looks like Gibbs state anyway. But that's not the way of Gibbs sampling that you would want to do, I guess.
No. I mean, yeah, you can almost do the same thing for classical like NP-hard problems because you can just try and at least sample a spin. But this sounds like not great because like most likely you guys end up in the very thermal like you're just going. It's very unlikely you can go far in the low energy states.
Right, I see. Yeah, that's right. Yeah,
because the energy distribution actually have a tail.
It's a Gaussian distribution, right? Yeah,
and then this tail is what you're interested in.
Yeah, fair enough.
And so the question is how to get there. So you need to perform some random walk that tries to go like sequentially lower the energy. And then if things are nicely connected, you can just keep going down.
Right. But just got it. Okay. Thanks.
David, do you have any thoughts?
Yeah, thanks, Anthony, for a wonderful talk. I think it's fascinating that there's a kind of developing framework for proving this kind of rapid convergence to the Gibbs state in certain cases. And I'm looking forward to the future development of sort of importing the tools that are available in the classical setting. Like, I don't know, I mean, Anthony, if there's a conductance type bound or things along those lines that could be applied to establish rapid convergence for certain models of interest. I mean, in particular, like, and maybe this also relates to the questions about quantum Monte Carlo. I mean, so it is the case that for the ferromagnetic Ising model classically, there is a classical Markov chain that converges to the Gibbs distribution, and that can be generalized. Was generalized by Bravi to the transverse field ferromagnetic Ising model because it doesn't have a sign problem, and therefore the Gibbs state has a classical probabilistic representation when you expand e to the minus beta h as a in Schroeder-Suzuki. The path integral has a positive representation as a distribution over paths. And for problems without a sign problem, you have a distribution over paths, and you can try to apply the classical Markov chain Monte Carlo to that distribution over paths and prove rapid convergence that way. But it seems to me like it would be really amazing if you could take a ferromagnetic model that is not that has a sign problem, and use use this kind of quantum Markov chain and establish convergence. So to me, it seems like a kind of an area that's ripe for a lot of different interesting directions that haven't been explored yet. And I really appreciate the kind of amazing fundamental contributions that were made in this work.
Great. Thanks, David. Andras, do you have any thoughts or or different way of understanding parts of this? What's your?
Yeah, well, thank you for the invitation and for the nice talk, Anthony. So for me, this talk and this whole project was about learning a lot of physics. I'm coming from more of a quantum algorithm side, and so for me, it's exploring all these physical ideas and tools, and I find it very fascinating. And I think that questions like this are very interesting from the perspective that they are touching parts that are algorithmic difficulties that quantum algorithms people work on, and then also physical side of problems where like really the quantum physics side and those kind of questions pop up, and somehow to come up with an algorithm simulating these dynamics or finds a Gibbs state, prepares a Gibbs state quickly, kind of needs both of these words. And I'm interested to see how ideas start to propagate. And then I think, I mean, lots of these ideas, of course, in quantum computing already like propagated from one side to the other, but I think there is still room for that. There is, for example, this tool, this quantum operator Fourier transform. Now, this is, one can view it as just phase estimation, and well, just quantum Fourier transform or something, you can view it as phase estimation. I mean, the circuit is just that, if you wish to say. But on the other hand, it is a different perspective on these things. And then you start to think about phase estimation and operator space, and that has different properties. And if you understand that way of looking at this, that can give you new insights. And I am curious to see if this new way of looking at these subroutines will lead to other algorithmic improvements elsewhere. So I'm really fascinated by this kind of interconnection between these like two sides of quantum computing, and I think we can gain a lot by connecting more of these questions.
So actually, I was curious. You know, this operator Fourier transform that you mentioned. So were you able to get a different view of it? You know, from a more algorithmic computational viewpoint, is that thread still? You know, are you still pulling on that thread? And
well, I mean, one way of looking at it is just a little bit like you can just vectorize that matrix and think about as a Fourier transform of this vectorized object. Mm-hmm. But then the interesting thing is that what you get out of it is still an operator. It's not a state, and so there are certain things that may be impossible. If you are working with states, then you have some abstractions that maybe are not present when you are working with operators that are just some action on quantum states. So maybe this is like one way how we circumstance with some differences, but I guess, I mean, there's still, we could still understand it better, I guess.
Mm-hmm. Okay, great. I had a question, Anthony, going back to something you said, which I don't know if I completely understand, you know, the statement or its implications, but it seems very interesting. So you said, well, look, you know, in terms of the rejection sampling, you know, you have to use Marriott-Watrous if you're in the discrete case. But you know, once you make it continuous, it all takes care of itself. And so somehow to me, I don't really understand that statement completely. You know, it seems like getting something for nothing. And so what's going on there? I mean, are you saying that you know, all this Marriott-Watrous you can just get rid of totally, you know, and just move to continuous time, and surely there's a penalty to pay there, right?
Yeah, I'll try to say something, and maybe Andras can supplement more of the algorithmic details to it. So it seems that originally there's some proposal of doing Metropolis using Marriott-Watrous. And then the problem they encounter is that when your energies actually have continuous, when the energy can distribute continuously, you don't know how to cut the two things. Like, sometimes things would just be right in the middle, and you don't know if the energy is like here or there. And that, yes, you can kind of grind through the calculation, and it just give you some blow up in complexity. And I think right now we still don't know how to make it work, even borrowing from this continuous picture. But then somehow, like, okay, so we're still trying to understand why this continuous thing is so nice. And yeah, Andras, if you want to add more.
Yeah, I guess we are still in the process of understanding it. I was actually just thinking about this, like how deeply it relates to each other, like this continuous versus discrete one today. And so there is something Zeno-like effect going on here. We actually have an implementation of this Lindbladian evolution by a weak measurement. And then it's very reminiscent. So one way of doing is kind of just going in hard, do the jump, and then try to go back. And then it's difficult. And then what we do in this weak measurement gadget instead is do the jump, but accept the jump only with a tiny probability, even if it was a successful jump. And then uncompute. And it turns out that when you make some kind of delta strong jump, you only make a delta square issue in reverting. So it's a bit like a quantum Zeno effect. So if you only like measure weakly, then going back, you only make kind of the trivial reversion of the measurement, only makes a tiny error, and then just scale down delta, and then this is how it happens. and then you can understand this Lindblad operation as just a limit of this weaker and weaker measurement repeated for longer and longer times.
Okay.
So Andras, does it relate to your quantum Lewis local lemma algorithm, or it's different flavor?
I was also thinking about this today during lunch, and it's a bit different. Somehow in that case, you need to modify the accept branch, and then that's the issue. And here kind of the issue is doing the rejection. Somehow it's a bit different. Certainly there is a relation, but it's also has some fundamental differences. Well, and just like one small comment on this, that Toby Hewitt has some very interesting paper coming out last week, and it also uses some kind of weak measurement like ideas to handle this non-commuting Hamiltonians ground state preparation. And so it's interesting how these weak measurements pop up in all these non-commutative settings and give you something. So maybe there is a more like fundamental connection between them, but that's still to be like understood better.
I did have one. So my initial response was about polynomial time algorithms and the optimism for that. But I also have a kind of comment, Anthony, about the kind of like I mean, I think you said the mysteries of low energy states, and the kind of you know, in your picture you had this kind of like worst case QMA hard, and you know that's bad, and then over here we have polynomial time algorithms, and that's good, and of course I don't disagree with that. But I think there is also a mystery above and beyond QMA hardness for these Gibbs states, because you know, yes, it's QMA hard, but what is the complexity of preparing the Gibbs state and computing expected values with respect to it? I mean, this is something we asked in our paper from last year, but certainly did not resolve. And I think, you know, for example, many physicists have been interested in the question, you know, in relation to certain questions about black holes, I think, the question of, can you design a local Hamiltonian whose ground state is the purified Gibbs state? And, you know, that's really a complexity theory question. Like, is preparing Gibbs states of the same complexity as the local Hamiltonian problem? I mean, roughly speaking. And, you know, is QMA the worst it can get? And so my comment is just that I think there's even more mystery than maybe was on the slide.
One thing I can add, like regarding preparing purified Gibbs states, is that our algorithm, you can, I mean, I guess the standard quantization scheme is that if you have Lindbladian that's thermalized Gibbs state, you can purify it to get the algorithm that prepared the purified Gibbs state. So at least if the Hamiltonian, I guess this Markov chain dynamic itself is nice, then the purified Gibbs state is also easy. But then it will be the ground state of this Lindbladian, so it's like some horrible operator. It's not really like a local Hamiltonian in that case.
Yeah, so I think the best upper bound we have for like computing expected values in a Gibbs state, I mean, is sort of sharp p-like. You know, I think it's sharp p, and I don't think we have a better upper bound on the complexity of that quantity.
Sharp p. I see.
So we showed in our paper that additively approximating Pauli expected values in a Gibbs state is as hard as relative error approximation of the partition function. And, you know, that's as hard as counting the number of witnesses of a QMA verifier to some relative error. And, you know, those problems are all in some class that is of unknown complexity between QMA and sharp p. So I guess I also kind of wonder, Anthony, like to what extent your these new results about Lindbladians and so on can address these sorts of complexity theory questions that are even not even about efficient computation, but just about the place of thermalization amongst the other problems we know that are hard, like the local Hamiltonian problem and so on.
Yeah, I think that would definitely require a better understanding of mixing time. And how that differs from a classical case. I mean, people seem to have studied spin glass for a long time, and they have all these nice classical picture of like a local minimum, etc., and kind of connect it to complexity. But yeah, right now I don't know how those picture would change in a quantum picture, because it seems like you want to go to energy basis, but you still care about local operators. So I don't know how they interplay, or how this local minimum kind of manifests itself in these algorithms. That somehow these algorithms get stuck in some way whenever some condition happens. Like they have lots of quantum local minimum, and I have no idea what those should look like.
Yeah, I guess I'm just making a slightly different point, because it's true that it's hard to find the low energy states of a spin glass. But computing the partition function or thermal averages is not much harder than that, because by Stockmeyer, it's in the third level of the polynomial hierarchy in BPP with an oracle for NP. So the partition function problem for classical systems is sort of understood because it's NP hard and not much harder than NP. It's in this third level of the polynomial hierarchy to compute a relative error estimate of the partition function. Whereas for quantum systems, that question and the question of additively approximating thermal expected values, like if you had the Gibbs state computing the expected value, we don't know the complexity of that, of those problems.
Mm-hmm.
So sorry, David, I'm not sure I understand. Are you saying these methods might help you show hardness, or that you're thinking it might be easy?
Oh no, I mean so certainly computing in the worst case, as Anthony said, they're in the worst case these problems are QMA hard. So for example, computing expected values of a Pauli operator in the Gibbs state is a hard problem.
Sure.
But I'm interested in what is exactly the hardness of that problem. Is it more like QMA or more like sharp P? And so any kind of new understanding of how we can prepare Gibbs states, or I was also interested in, for example, this Brandao and others paper on quantum imaginary time evolution, which had seemed to say some interesting things about Gibbs state preparation. So anytime I hear about new developments in this area, I kind of wonder to what extent they can be deployed, not just for efficient algorithms, but also for our understanding of the worst case complexity of these problems.
Mm-hmm.
So can I ask a question? Oh, sorry. Yeah. So if A is a local operator, is it known whether it can or cannot satisfy ETH?
There are lots of numerics for
What
specific.
Suggest? If I just have a it's just a one Pauli operator.
Yeah, that's. I believe it satisfies ETH in certain models.
Satisfies ETH.
I think I think people do that. I think even you can take lots of them and they all seem to satisfy ETH. But the precise condition is very hard, because it's very hard to check if something is a random matrix. You can only do some tests. But then all these tests agree with random matrix.
Is it clear how wide the width depend on the choice of the Pauli?
So you can definitely bounce, because the local Pauli doesn't change energy by too much. So you can basically restrict it to a small window. But but below that, it's not very clear.
Thanks.
Because it just requires diagonalizing the matrix, and you can do 20 spins, 15, 20 spins.
Okay. Any final thoughts?
So I had a question, but I don't know. Does someone else want to share something before I want to? I mean, maybe I'll just try.
Right.
So your second part of the result says that assuming ETH, this quantum Markov chain converges fast, but we know that there are some complexity theory reasons for certain Gibbs states to be hard to prepare. So does your result give a complexity theoretic refutation of ETH in some systems? Like I guess there's a big open question out there. Does MBL exist or not? Things like that. It's widely debated, but it seems like you're coming with a different angle here that, look, here's a complexity theory reason why ETH should not hold in many systems out there.
Yeah, I think that definitely sounds plausible. I mean, like heuristic, I think just depends how you want to set out the problem. Like if you want to, because if you want to certify something, it's definitely not ETH. Then it's kind of related to like how do you check the gap of expander kind of questions. I don't think that's always easy. I mean, it depends on what. Yeah, sometimes just checking things are just quite hard. Especially like as content expander, I think there's some existing work that checking content expander gap isn't QMA hard, if I remember correctly.
Right. No. So no, what I was asking, I guess, is in terms of exhibiting local Hamiltonian systems which violate ETH. I mean, my understanding is that somehow people don't believe anymore that many-body localization is real because it's not stable under perturbations. But again, physicists should correct me if I'm wrong. This is my picking up things from having lunch with people. So if ETH is always the stable point of everything, then does it mean that complexity theoretic hardness is not stable? I mean, there are all sorts of questions you can ask, and I was wondering at what level they've already been answered by your work.
So let me now put on a physicist hat and say something physicsy. So what's expected is that I think most systems at high temperature are pretty much chaotic unless you make them very integrable. But integrable, you can perturb it, maybe it breaks, maybe it's like quasi-integrable, maybe. But then most likely, lots of things are just very chaotic at high temperature. And then at low temperature, it might become more solvable in some way. Like if a gap system, then you might have this particle picture, like you have some excitations, like 1 particle, 2 particle. That's not quite ETH. Or if you have a spin glass system, which is more exotic, but then it might just become a very hard combinatorial problem kind of below a certain temperature. Yeah, so I think there are definitely things beyond ETH. And I would believe that if you try to put like some complexity, some very high complexity state, it shouldn't mix. Yeah.
Yeah, thanks.
Great.
If I may, I have like another comment or question that is like going in a different direction than all these questions. So can your first result on sampling tell you anything, it's a long shot, like tell you anything on classification of phases? Because you have essentially a result that, holds for different values of beta, even going to the ground state, right? And, there's a whole field of people trying to, well, first of all, if you just focus on closed systems, there's a bunch of people that have been working on classification of phases for a while there. And there's not a clear agreement on the definition of how to define different phases for open systems and how to classify them. So there are many different attempts in the last few years in the literature. And some of them have to do just with decay of correlations on Gibbs states of ground states of Hamiltonians. Some others have to do with different values for the mixing time. And I don't know if the bound that you're obtaining for the sampling in your result could give you some information there. I think this is kind of related to the question of how tight is that estimation. So because you have an estimation there, so do you know if it's tight for certain values of beta and for some other values of beta it breaks, and then you have like some form of phase transition there or something like that?
Yeah, so for classifying phases, I have this thing about it. I definitely heard people talking about like how yeah, so that let me think about it later. But for the second part, So right now, the most mysterious thing that could have created that probably encode all the interesting physics is the mixing time. All the other parameters are just very simple. It's just like linear dependence and like inverse 1 over epsilon. I don't think those encode too much of physics. But this mixing time is really mysterious. And definitely you can imagine this mixing time would start diverging if maybe like if you get very close to some temperature and then something else happens. But that's at least definitely one thing that could happen, and you can tell you can see very clearly.
Okay, thanks.
Yeah, so sorry, but just to go ahead with that. So the mixing time has to do with these jumps which don't come from the Hamiltonian, right? So it's something that you're picking separately. So how intrinsic is it to the physical system?
Yes. It's not clear. Practically, I might guess like if you had poly XYZ locally, that it should work. But maybe sometimes you have to do something more fancy, like maybe you have to like flip two things at the same time in a very distant location. Maybe that will help, but I don't know. Like I think, yeah, it largely depends on the system. Yeah, but if you just have few body operators, that's like there are not too many of them, so you might as well just throw all of them in. And I guess the algorithm doesn't depend so much on the number of jumps you want to use. It's like log A, not log number of things. Because
Great. Anybody else?
I could ask one more, but I don't know how much time is allotted.
No, it's fine. It's fine. We can have one more question.
Okay, well, I was, following up on Anurag's earlier question about the refuting ETH, for certain systems where you shouldn't be able to prepare the ground state or thermal state. It seems to me like probably physicists would not tell you that ETH is exactly satisfied in any system, right? And probably there's some natural notion of approximate ETH. And I wonder to what, how delicate is your convergence proof? I mean, if you take the natural notion of approximate ETH, whatever that may be, first of all, do you know what it is? And second of all, do you think your proof adapts well to the approximate version?
Yeah, I think these proofs are robust, but that's also why it's very nasty, because these depend on so many but it's very robust. And these expander properties, right. So another answer to the question is that, okay, what is this quantity, like weak ETH? You can really think of it as some kind of like expander gap of a bunch of cross operators. Or it's a gap, so perturb a little bit, definitely stable if you don't perturb it too much. So that's one kinetic quantity, and I'm sure it's pretty robust. You can even prove that for generic random matrices, it always have the gap. And further, like if you say, what would be a sensible definition of ETH that, without exactly addressing individual energies, definitely I think you can use some low moment approximation for the quantities you wanted. Because gap is roughly, to access the gap, you roughly just need like a degree log D polynomial. So definitely many low moment things could capture ETH already.
Great. Thanks very much. So, well, thanks, Anthony, for a great talk, and thank you, Angela, Anurag, Andras, and David for a great panel. So, next week we won't have the colloquium. It's both the Fox deadline, but also for people with kids, it's spring break. So we'll skip next week and we'll resume again the week after. So see you then, and thank you, everybody.
Thanks.
Thank you. Bye.
Bye.